And welcome to today's Teardown Sessions. I have yet another exciting space guest for you this week, Zeke, who will be talking to you about ground stations and antenna and all sorts of goodness. But before we do that, as usual, I'm going to bring on some of the things that we're doing at Crowd Supply. All right, so right now at Crowd Supply, what is most on my mind is the conference happening June 21st through 23rd. It's an awesome hardware conference that focuses on open source. We have lots of hacking, lots of hacker art, we have lots of workshops, we have all sorts of fun things. So if you're in the area or if you fancy visiting Portland in June this year, please check that out. We're still on early bird pricing and our CFP is still open. So if you want to do a talk or give a workshop, now is a good time to tell us about that. Okay, so also going on at Crowd Supply, we have a couple of Crowd Supply. We've got a few campaigns going on at the moment. We've got 3 ESP32 campaigns at the moment, actually. So this one's came out the gate pretty quickly, and I've seen this floating around the internet as well. So this is Walter, which is an ESP32 S3 module with all sorts of goodies, including GNSS and LTE. This is a very nicely designed and executed with a very small form factor for what it's actually doing there. So that's only just launched and it's already doubled its goal. So if you're interested in this, go and check it out now. 34 days left. Another ESP32 device that we've got, this time using a RISC-V microcontroller as well, also has lots of goodies on board. We've got Zigbee, we got Wi-Fi, BLE, etc., etc. It's also hit its goal already, but we've still got 2 weeks of that left. So if you fancy an ESP32 dev board that uses RISC-V, I would definitely check this out. Plus, it's got a cute little PCB design there as well. Good job. And then the final ESP32 device that we've got going on at the moment, I told you it was ESP32 themed this week, is a little PD analyzer and power supply that makes use of an ESP32. And again, obviously, Wi-Fi from BLE, and as you'd expect from the ESP32. And again, they've already hit their goal. But if you fancy supporting this open source PD analyzer, you should go check that out as well. Now, coming soon at Crowd Supply, we spoke to the creator of this device, this triple filtered LNA, 2 weeks ago on the stream. So if you're interested in today's stream, you'll probably be also interested in the stream we did a couple of weeks ago. So I did want to just point this out. This is a CubeSat focused LNA board made by some really awesome folks. So that's coming soon. Now, before I bring on my guest, I wanted to give a shout out to the sponsor of today's stream and also the people that introduced us to Zeke, who will be our guest today, Qorvo. So as per usual, they are partnering with us to help get the next generation of wireless solutions out into the world. So if you are creating a device that is using a Qorvo component and you're looking at crowdfunding it, we do have this program that will get you money off your campaign and will also get you additional support from Qorvo. So definitely worth knowing about. So thanks. So without further ado, I'm going to bring on my guest today, who is Zeke KJ7NLL, YouTuber, coder, hardware designer, all sorts of things. Let me just bring him on and I'll let him introduce himself. There we go. Hello, Zeke. Nice to meet you. Thank you for coming along onto the show. Would you like to introduce yourself to the people at home?
So I'm Zeke KJ7NLL, and I have been working on a project to contact the International Space Station, and I have continuously tried to contact them a lot whenever the ISS is overhead, and I've made a bunch of really cool contacts, but I have not contacted anyone on the ISS yet. I'm also working on another project, my desktop satellite tracker, right here. So can you
yeah, we can see that. Yeah. I'm going to spotlight you so they can get a better view of that. There we go. Look at that. So yeah, go on.
And it's also using an ESP32 chip right here, which you were mentioning.
Yep. It's a popular one. It's ESP32 day today, clearly.
Yeah.
And I know that we're going to get to have a little look at some of the code behind that satellite tracker as well, aren't we, later on today? So I'm very excited to hear that. But before we dive into that, do you want to tell us a little bit of the history behind how you became involved in tracking satellites. I was watching a talk that you did recently, and you were talking about your whole journey through the ham radio sphere towards the communication with the ISS. So do you want to tell people a little bit about how that came about?
Yeah, so when I was 8 years old, I wanted to contact the International Space Station. So I asked my dad, how can I do that? And he's like, I don't know. So we got online and we searched around and we found this place called Eris. And they managed to get a ham radio onto the ISS. So I studied and took the test, and I didn't pass the first time. So I studied again, and I took it again, and I didn't pass again.
Oh, no.
So then I studied even more and took the test a third and final time, and I passed with a higher score than my dad.
Amazing. That's great to hear. Perseverance absolutely pays off. Very cool. And what did you learn? I've not taken the ham radio test. What do you actually have to do? What is that? Is it a written test? Is there a practical element? What's the deal?
So it's a written test with 35 questions each. And so if you get more than 25 questions right, then you pass.
Okay.
And there's 3 different license levels. So you have technician, then general, then amateur extra. I'm a general class licensed, and then at 9 years old, I passed that.
What's the difference between the 3 types of licenses?
So the difference between the 3 types of licenses is the first one, the technician, allows you to use only a few bands. So the 2 meter, the 70 centimeter, and really anything above that. But the high frequency and the low frequency and the very low frequency stuff, you need the general class license and the amateur extra license for that.
Okay. And why did you choose the license that you've got? What was it that you wanted to do that you weren't able to do with a different type of license?
So when I got my technician, because you have to get your technician before you can get your general,
so that's
before
step
you
1.
can get your extra. So yeah. And then so you just keep advancing. There wasn't really anything I wanted to do, except I did get a HF radio where you like solder the components together on your own for one of my birthdays.
That's a great birthday present.
That was my very first video on YouTube.
Oh, really? Oh, that's delightful. I'm kind of jealous. I've never had a birthday present like
that. So you solder the components together, and it's not even finished yet because I wanted to make a 11-band extension because it only supports 6 bands.
Okay.
So we could.
And how are you going to do that? Are you going to get a different add-on board for it, or are you making your own adjustments?
So I'm pretty good at designing my own circuit boards.
Yeah, which I'm interested in hearing about for sure. Can we talk a little bit about that? Actually?
Oh yeah, sure.
Yeah. So tell me about your first circuit board, and tell me all about the software that you're using and your learning journey there. It's such a useful skill, so I'd be interested to hear how you've acquired it.
So my very first low noise amplifier board, which was an LNA, I don't have it here with me. But sounds like I will be getting it shortly. So my low noise amplifier board was the very first board that I made, and it was very small. It's about this big, and it uses a Qorvo QPL 9547 amplifier chip.
Nice.
So this is a.
Let me spotlight you so we can get. Let me just spotlight you. Look at that. That's the very first board that you designed, huh? You can put your hand behind the board to block out your face, and it might focus. Your camera could, it's like that's a beauty blogger trick. Oh, look at that. That's even better. You've got that. Perfect. Nice. I can see really well now. So talk us through this board. What's on here?
So here we have a relay right here. We have our QPL 9547 chip right there. And this LNA is not labeled, so it looks like one of the good ones.
Tell me, is it one of the good ones, or is it tricking you?
I think it is one of the good ones.
Okay.
Because it doesn't have any writing on it and it looks very neat. Although there is no label on it. So
okay.
One of the good ones is up in the antenna, which I'd like to show you.
Yeah.
I'd have to pull that up. Anyway, so the antenna outside was my original tracker to track satellites to contact the International Space Station. And so this was used as a low noise amplifier to get those signals from the ISS. And it took a year to make and design this. So,
Was this your first revision?
This?
Yeah.
No. It took a year to get to this.
Yeah. Wow. And then what kind of changes were you making? Was it to optimize, or were you making errors that just weren't working? Like, what were you working on for that first year?
Yeah, so what we were working on is the matching circuit for it, because it's supposed to be internally matched, but this chip is not designed for what we were using it for. It's designed for the very high frequencies, like
oh, really?
Or ultra high frequencies, like 13 centimeter band or Wi-Fi. But we wanted to use it for like really low frequencies, like 2 meter.
And why did you choose this component? If it was
just
designed for something else?
Well, there aren't really any LNA chips that are designed for that, unless you like go and buy it yourself. But I wanted to make it myself. So here we have a low noise amplifier chip. And it took a year to get here because to finally figure out how to optimize correctly. And I was using Cadence's Microwave Office for simulation.
Oh, Microwave Office, interesting. And what were you using for the design itself? Did you use KiCad or?
To design this board, I used Microwave Office as well.
Oh, really? Oh, okay. I didn't realize that you could do PCB design inside of it as well as testing.
Oh, yeah.
Interesting. Very cool. Okay, awesome. And what other boards have you been working on? So you've got, I believe, 2 LNAs, right? So is that correct?
We have a 70 centimeter and a 2 meter, but there were 2 different revisions for this board. So there was an old revision, and really all those revisions happened on the back, right here.
Yeah.
So here we have.
Oh, nice! I can see you've got your call sign on the board on the silk screen there. That's nice.
Oh yeah, I always try to
that's cool. That's cool.
Do that on all the boards I make. So
yeah, good. I like a signed board.
Oh yeah, here. So these are other boards that I have made.
Oh wow, these are really cool as well. Is that an OshPark board?
No. So these were all ordered on JLC PCB.
Okay.
So,
the purple was tricking me.
Yeah.
Nice.
So
what? Talk me through what these are.
So this is the rocket board. I have been designing this rocket board. I designed it. Actually, this is a really long time ago. It is a triplexer. It was going to be a triplexer. Now it's a diplexer. Okay. Because I couldn't get it to match with 3 bands, so 2 worked. And it was going to be a hexplexer, but that just never worked with 6 bands going into 1 wire.
No, that's is that rocket shaped as well?
Okay. Yes, it is rocket shaped. I like to design my board. This is a robot board.
Oh, yes, so it is. Now you've said that's very obvious that it does look like a robot face.
And I surprised my mom with earrings because that little hole in the top can be used for earrings.
I love it. I do love a PCB earring, I have to say.
Yeah, we sent them out to everyone.
Nice.
So here it was really hard to get the antenna matched to 50 ohms because it kept melting. With the amount of power that we were sending through it.
Like literally melting?
Yeah, so I'll need some...
What parts were melting?
Just like the tunable capacitors. So we changed these mica caps.
Yeah, I see them.
We changed these mica caps, which would handle the heat.
And what's the functionality of the blue wire on that board?
So the reason for blue wire is it's not necessarily the color, but it's pretty too. But
yeah, for sure.
The reason for the blue wire is because it's actually jeweler's wire, and RF tends to flow on the outside of wire and not the inside as much. So it's silver coated, and silver is extremely conductive, more conductive than copper. Which means that the RF, because it's going to tend to the outside, it's going to be less lossy. So that's why we're using this
jeweler's wire. Very cool. That's a really awesome tip that I absolutely didn't know. So jeweler's wire has an external, well, two things there that I didn't know. Number one is that RF tends to travel on the outside of the wire. I'm not an RF engineer. And the other thing that I didn't know is that jeweler's wire has that coating of the silver. I feel like that's a tip that I'm definitely going to use in the future.
Not all jeweler's wire. You have to
really?
get coated jeweler's wire.
Okay. Specialist jeweler's wire. And where do you get that? Where do you source your jeweler's wire from?
Just Amazon.
Just Amazon or eBay. Okay, cool. Interesting. All right, cool. Carry on. Tell me more about your designs.
So here we have another Qorvo thing here. It's our low noise amplifier board for the 13 centimeter band for getting a picture from OreSat.
Ah, yes. I was actually going to ask you to explain the difference, why you'd have the two different LNAs. Yeah, if you could say why you might need those, in what instances you'd need those two, that would be helpful, I think, for people.
So this antenna here is what I was going to use. Actually, this is the original antenna I was going to use to try to to try to receive signals from OreSat 0, because they have a camera up there and I wanted to receive signals from it. Yeah.
And how does one receive signals from it? How is it different from receiving other types of information?
So it comes in packet form. It actually comes down in Wi-Fi, so you have to decode it.
On Wi-Fi? Oh, interesting. I didn't know that.
Yeah, and so I made this helical antenna to try and do that, but I never got a signal from OreSat. So
we'll have to ask Andrew what Andrew Greenberg, for those who don't know, is one of the people behind OreSat, who's also a regular on this stream and will be coming on in the next few months. So I'll have to make sure that we pose all of your questions to him about why you haven't been able to pick up your any of the signals with your antenna. Can you tell me a bit more about the design of the antenna that you've got in your hand? Because it's an intriguing design. So just for context, on the last stream, we spoke quite a lot about Jaeger antennae, and I'd be really interested to know if you could explain the difference between the kind of antennae that you're using and like the more traditional, I guess the Jaeger antennae that you see quite a lot in hobbyist space signal finding. Yeah.
So this is a helix antenna. So it's helical shaped, which means it's circularly polarized and it can receive signals in any polarization. Whereas a Yagi antenna, if it's not crossed, is only horizontally or vertically or whatever polarization you choose. And so this is circularly polarized, so it can receive any signal from any polarization, because if one of your Yagis is pointed like this and one of them is pointed like this, it's like trying to catch a frisbee that like this, that's thrown horizontally. So it's trying to catch a frisbee vertically that's thrown horizontally, and you won't be able to catch it.
That's a good example.
So this is like catching it in a bucket. It doesn't matter what angle it's thrown at. It'll always catch it.
And does that affect anything else? Like, so why would somebody use a Yagi instead of one of these helical antennae?
Well, helical antennas, I think they require a lot more wire, and they're huge. They're ridiculously large. The one outside is 10 feet long, because the circumference of the winding, well, the more directional you get is the more windings you have, and the circumference of the winding, so each winding here, each rotation is 13 centimeters long. Oh.
So it has to be very exact then, the specifications. So
yeah, if it's too small, it will act as a rubber duck.
You're going to have to explain what you mean there.
All right, this is a rubber duck antenna. You usually see these on like cars and things. It's just
okay.
It's just like a wire that's wrapped really tight around a thing to make it electrically longer. Because this is much less than 13 centimeters.
I've never heard that called a rubber duck before.
Yeah, this is what we learned in our hand tests. It's called a rubber duck antenna.
Oh my gosh, I like it. Yeah. Okay, carry on.
So this is a helical antenna, and it's directional too. But it's directional off both sides, so you need this huge reflector. And unlike a Yagi antenna, where the reflector is just horizontal, because this is circularly polarized, you need to have a reflector that's 13 centimeters all the way around.
I see. Interesting.
So this antenna just nicely clips onto my tracker.
Yes. I'm excited to hear about this tracker. Me solo, yeah.
It clips on like that. And it's trying to keep its position to point it at the sun. So it's tracking the sun right now. And so it might be receiving signals from the sun, but I've got a metal roof, so.
You're not going to get much luck.
Yeah.
And so do you want to show us a little bit more of the, so you've got the words, Helen. Do you want us to show a little bit more of that desktop antenna and and tell us a little bit more about that tracking system?
Sure. So this tracker here, it is a desktop satellite tracker, and you can control it using this menu. What happened?
Oh,
there.
We're back.
All right. So you can control it using this tracker and these LCD screen.
So you see, when you say the tracker, you're referring to the green board. That's the tracker part of
the whole thing is the tracker. The
Okay.
green board is the control system for the tracker.
So you've got three. Yeah, I was going to say, what's the central piece there? So we've talked about the antenna. We know that this is the control board, and then the stem. What's going on here? So
there's another board in here which houses a magnetometer.
And are you using that for getting like compass, like cardinal positions, or?
Yeah, so it's a compass basically, and it gets the position for the antenna to point. However, if I get something magnetic.
I was going to say, how susceptible to interference is it? I like the fact that did you just use a fidget spinner to demonstrate that? I like it.
Yeah, except it's not very magnetic.
No, they're not particularly. So yeah, I mean, I was going to say, so that does depend on interference. You need to make sure that that's not anywhere near something that's magnetic in order for it to work correctly. Yeah.
Yeah, and it's a real problem because there's rebar and concrete sometimes, and that can really affect it.
Yeah.
And then up here is not really affected by magnetic disturbances because this is an accelerometer. It just measures gravity. So unless you've got a really heavy object, it will measure correctly, like another object the size of the Earth.
Yeah. Or if you're on a different planet, it might act up.
Yeah.
But yeah, that's cool. And what are the motors those like servo motors that you've got in there that are, or what are they, steppers? What kind of motors are you using to control them?
So they're actually just DC 5-volt motors.
Oh, just straight up and down DC 5-volt. And that's enough. How is that actuating the arm? What's the mechanism there that you're using?
So here we have a double-stage planetary gear system. Maybe I can show you the bottom, except it'll freak out. So
sorry to freak your electronics out with my questions.
Yeah. So here we have a dual-stage planetary gear system here, which gears it down from 50 RPM to very slow. It was originally designed for 400 RPM, but it's not really, it was really fast, so that got turned down.
Would you be able to, before we move on from that, would you be able to briefly explain what a planetary gear system does for those people who might not be familiar?
Yeah, let me pull it up in TinkerCAD, which is what I've been using to design it.
Oh, perfect.
So we just go to TinkerCAD here.
Let me know when you're ready for me to share the screen. Oh, let me pull myself out. All right, let me know when you've got a screen ready for me to share.
Firefox is much better than Chrome at this.
I mean, But unfortunately, the streaming software that we use prefers Chrome, which I'm not a fan of either, but we do what we must.
I found that it works better in not Chrome in Firefox. It wasn't seeing my microphone in Chrome.
Really? Well, it's temperamental. And also, you know what? I've not tried it with the latest update of Firefox either. It was about a year ago. So, and I hear it's had a fairly significant update recently. So maybe I'll go back to my preferred browser. I've been suffering through Chrome, but you've given me hope today.
Okay. Allow.
Here we go.
Okay, my screen.
Here we go. I've got your screen. Here is TinkerCAD. Tell us what we're looking at here.
So TinkerCAD here, if I can full screen it.
Oh, yeah, I can full screen it. There we go.
There. So here's TinkerCAD, and these are all the parts that make it up. So here's a mock-up of the tracker itself.
Oh, this is super interesting.
Yeah, you can see those motors there.
Yep. Oh, it's on a little worm gear.
Yeah, so for the top, it's just a worm gear, but for the bottom, if I hide a bunch of things.
Yeah, that's what I'm interested in. This bottom bit, and
I have to hide a billion things, and then
this is a lot of work. Is this based off of somebody else's prior work that's open source, or did you design this from scratch?
I designed this from scratch.
Wow.
Not in Scratch, from scratch.
Yeah. Not in, I mean, that would be quite. Could you even do that in Scratch? No, you.
Well, actually, sort of. You could.
Oh, really?
Because TinkerCAD has a Scratch. I'll have to show you that earlier. It's how
TinkerCAD has a Scratch plugin these days. Does it really?
Yeah, and
fascinating.
Actually,
that's
back
really
to my
cool.
Video. Back to my video.
Oh, for your video. Yep. Hang on a second. We got you. Here we are.
So here we have this, and
wrong one.
This was designed in TinkerCAD code blocks, which is Scratch based.
No, wow, that's so interesting. I didn't know you could do Scratch TinkerCAD.
So that's how we made this. It's a new feature.
Yeah, that's really cool.
And then so this is the planetary gear system. Back to
yep.
Screen here. So planetary gear system, you've got 6 gears here, and they're carriers. And it was very hard to find the correct gears with the correct gear generator. I did not make the gear generator, by the way. But to find the correct gears with the correct gear generator to make this work. And then also to get the 3D printer to print accurately with...
I was going to ask, that was going to be my next question. How accurate is your, and what 3D printer are you using in order to actually make this? Because this is quite precision, or is it not? Is there a little bit of leeway?
There's a little bit, but you have to be pretty precise to do it.
Mm-hmm.
It is supposed to be accurate within like 0.5 millimeter or something, or 0.2 millimeters. Well, the print head probably is accurate that much, but the not print head is probably, well, not probably. I know from experience that it is not very accurate. You have to make a bunch of tweaks in its slicer, which takes these STL models and makes it into something that you can 3D print.
What slicer do you use?
We use the Cure slicer because it's like it has a billion features that you can just use whenever you need to.
Yeah.
So we've got a profile for each different type of filament that I use. So
yeah, that was going to be another question as well. Yeah, what kind of? Yeah, I want to hear about your filament types, and I want to hear about the printer that you're using.
So I have a Tronxy X5SA 400 Pro printer back there.
Ooh.
So
Nice.
That's what prints everything. It's got a huge bed, which allows me to print these huge objects. 161 by 141. And this is pretty much at TinkerCAD's limits of design. So you can't really design anything more complicated than this.
I was going to say,
there's limits.
this is definitely the most complex TinkerCAD design I've ever seen.
And yeah, so some of the things that have to fit into other things are actually smaller than the other things they have to fit into.
Of
Or
course.
did I not make any sense? So back to my video.
Yep. Here we go. Do you want me to
Here we
spotlight
have
you? Yeah, there we go.
Yeah.
Yeah.
So here we have a gear and a peg that sticks into the gear.
Mm-hmm.
All right. Now this peg is designed bigger than the hole
Mm-hmm.
to get it to fit.
Yeah.
Because if this was like on a real machine that's like really, really accurate, that would not fit because this peg is designed larger than this hole. It would not fit into the hole. And I can't pull this out, so it became a desk toy joystick. And it was going to be a slip gear, so that if the gear got under too much stress, it would just slip.
Yeah.
But that never happened. It's just a normal gear now, as you can see.
I can.
Just a gear.
All right, let me take you back to there we are.
Yeah.
This gear. And these are positional rotators so at the top we've got you're tracking the sun with this because there's two positional things, right? There's the base bit and then there's the top bit. And what are the purposes of both of those?
So the top bit is just to move up and down, and the base is moving left and right. So if I plug this in, you can see it. Go back to my camera.
Mm-hmm.
So you can see how this one moves left and right, and the top moves up and down.
I do see. Yeah. And the particular gear ratios, are they designed for to make them work with planetary movements? You know, why are there so many? Why are there so many gears on the bottom bit?
So on the bottom, if you go back to my
TinkerCAD
screen share,
yep.
On the bottom here, there's 6 because we drive the bottom level.
Yeah.
Okay, so that gets driven.
Yeah.
And the outer is stationary, so it does not move.
Mm-hmm.
So this drives the carrier right here, which connects to this gear. Now, if I hide these other things, this gear is what attaches to those other gears. So it's basically a triangle that attaches to the bottom carrier. Okay.
Yeah.
And then that spins, and it spins the other gears on this. If I show it anything, it'll show everything, so I can't do that. But it will turn that, and then I wish I could show, but I can just move over to my other things here. It will turn this, which turns the tube.
Yeah.
Which I hid.
But we remember it.
Yeah.
So you unhid them one by one. That's very cool. And then also you got your little screen there, and then you've got a giant OK button. I'm assuming that's a button, or is it just,
that is supposed to be a button with up, down, left, right, except it never really worked out.
Okay. It's a decorative button at the moment. Yeah,
because I've been working on my slides for my science fair project.
Yeah, well, you're a busy individual. You haven't got time to do everything. And then we can see your ESP32 there on the right hand side.
And actually, let me take you to the if I can find this. Let me take you to KiCad.
You're a KiCadder, not a KiCadder.
I'm a KiCadder, yes. So here we have the circuit schematic for the baseboard, which is that huge circuit board.
Yeah, that's the one at the bottom of the device that you were just showing us, the ring-like PCB,
yes,
right? Yeah.
That. So here we have the ESP32,
nice.
And these are all the buttons. They connect in binary. So this is 1, 2, 3, 4, 5 in binary with these transistors connecting to 3 GPIOs on the ESP32. And then we have our USB plug here.
That's USB-C there, isn't it?
Yes.
Yeah.
So that's how it gets power and stuff.
Yeah, yeah. Are you using any? No, you're not. You're just using it for power and data.
Yeah, power and data.
Yeah, yeah. Okay, cool.
And then here I have an auto download chip, making it very easy to install new code onto it.
Oh, I see. Okay.
And then down here is the circle board connections. Now the circle board is really cool because back to my camera here.
Mm-hmm. I was. One second. I had my glasses on and I was peering at your schematic. I wasn't anywhere near my switcher.
All right.
There you go. All yours.
Oh, it's drifting. Anyway, so this here, if I just use wires to connect it, the wires would twist up. So we have contacts underneath this board here, which press onto these gold rings. Oh, and I'll show you that better with the schematic.
Yeah. That's great. Let me just switch back. There we go. Oh, fascinating.
So this is the circle board, and it just connects onto those rings. The colors are wrong, but as you can see, it's got those rings there.
Of course.
And then if I go to the baseboard, if it's open, I might have to open it. Double click. There.
Nice.
So if I go to here, the colors are wrong still, but if I go to the bottom, these are the components that press onto the circle board.
Yeah. And are you how reliable is that? Have you had any problems with that, or have you?
So to get the level correct for the sizing of them, that took a bit of work to get that to align. But once it was aligned, it's very reliable because there's 3 of them. So even if one comes off or something, it doesn't work anymore, the other 2 will still press.
What is this mechanical component that you're using here?
So they're like battery contacts, like what you would see in a phone for those batteries. So yeah.
Gosh, renders are so much better than they used to be. KiCad looks so. It looks great. It's not the right color, but it's still a good render.
Here.
Yeah.
Preferences.
Right.
Colors.
Oh wait.
Okay.
Nice.
There.
Nice.
There you go.
Nice.
So that's correct colors.
Yeah, that's really cool.
So that just puts onto that, and then in TinkerCAD, what was I here? In TinkerCAD, if I hide this, you'll notice that under here we have pressings here.
So you do, yeah.
And they make it so that it really has to press against them, and it won't just compress the gears down.
I see. Yeah. So you've got that little structural thing there in your 3D print as well.
And this build is entirely I2C based, so all of these components and stuff is entirely I2C based. So those four connectors on each connector is SCA. It's SCL, SDA, ground, and I left my
power
here, and 5 volts. So
yeah,
for the motors.
Yeah.
You really only need 3.3 volts. You can switch back to my camera now.
Yeah. Okey-doke. Hello. There we go. Let's remove your TinkerCAD. There we go. I can bring that in. Oh, I pressed remove instead of. Okay, we can share it again if we
I
need
removed
to.
it.
Oh, you did. Okay. Well, I thought I thought my finger had slipped and I did it incorrectly. But no, I'm glad it was you, not me.
All right. So that's TinkerCAD. Oh, right. I was gonna show you the TinkerCAD code blocks for the antenna.
Yes, you were. I'm looking forward to seeing that.
So if I go to code blocks here, helix generator. It'll
when
take
you were
forever to make.
That's fine. We can talk amongst ourselves while it's making. And what were you looking at as your reference designs when you were doing this? Were you just researching it with other people, or were you looking at other people's designs and then coming up with something that you'd like to make that's similar to others? You know, what was your motivation and what were your influences for this?
So for the helical antenna, that came from my outside antenna. And I think I have a picture of it.
Ooh.
I think pictures processed. Aha! Plenty of pictures, all for my presentation. If I can find the right one. Here. This might be it.
My camera's just decided that it didn't like being connected to my computer. I've got to reboot.
Oh, that's too bad.
That's fine. We can look at your code while I fix my camera. It's the beauty of live streams. It doesn't matter.
Yeah, all right. Let me share my screen because I think it's finished.
Cool.
3.
Okay, got it. I've got it. Here we are. Yeah.
So this is the code that makes it.
Oh my word! That's so interesting. This is so. This is so funny. Tell me. I've not seen the scratch for TinkerCAD before. Talk me through how to make it.
You've got all these things that you can add over here.
Yeah.
And so this antenna here, you enter your variables here, and they're used all over the place to make this result. And then in another actual 3D model for TinkerCAD, you turn that into the actual antenna, because you'll notice there's no hex grid down here, and this is extra tall than it has to be, and it takes 6 hours to print one of these. Now the funny thing is, if we go back to my camera here, this took 9 hours to print.
There we go. That took 9 hours to print. Okay.
And this one, which is like twice as long, took 6 hours to print. And why is that? Well, I'm guessing it's because when I did this one, notice how many there are. There's actually, because it twists, there's more than it actually is. Yeah. But there's 5 per rotation, and there's only 4 per rotation here. Yeah. So that's probably why. Also, I thought I was having problems with this. So you'll notice the difference in size of the reflector. Oh, I really do. Yeah, that's much different. Much different. Is that just standard PLA that you're using there? Yeah, just PLA. Yeah. So it's all we use, really, because we can use it and it doesn't smell. So we can use it in the basement. Yeah, we like it when it doesn't smell too bad. There we go. It doesn't smell at all. At all. No, yeah, for sure. Yeah. Unlike resin. And then I added the Fibonacci sequence here for the rotations here. Yes. So that's the Fibonacci numbers that allow you to make that spiral. It's quite elegant, actually. That was kind of the point. Good. I like to hear it. I like to hear somebody who's engineering with elegance in mind. Yeah, actually, that's one of the main things I think about when I'm designing things. Oh, really? Yeah, I try to make it as pretty as possible. So aesthetics are important to you and your design? Yes, it is. Like this, the tracker. Yeah. What were the aesthetic considerations you had when you were designing that tracker? So for the tracker, it keeps falling because of the newly made apparatus I made for the camera. Anyway, so this stick. It is very attractive, I have to say. I like the and I really enjoyed the design of the base as well. So this base was just going to be a small board on the side, but I thought it would be cool if it was nice and round all around it. And then
I
this
agree.
is rounded all over here. And it has a cutout here so you can see the gears and stuff. It was supposed to be clear because I wanted to see the gear interactions.
Yeah.
And this is clear too, except it's more translucent than transparent.
I feel like we should bring back translucent, transparent electronics casings. They had a heyday in like the Steve Jobs Mac years when you could see all the internals, and I definitely enjoy it when I can see the internals of my devices. So I appreciate your transparent offerings. Very cool. So you've got this piece of code that you've shown us here that was used to design this. There's also another piece of code that I was hoping that you'd show us how you actually control your base station. Base station. What am I talking about? The receiver. Yeah, exactly.
If I bring you over here, that was actually on this workspace. So if I middle click this, if I middle click this and middle click that there, and present that, we have code.
We have code. That's what I like to see. Tell us about your code here.
So this is all written in C, and so this is main.c. It's got quite a few lines of code, 2380, which is probably bigger than it should be because there's a lot of things here that could be turned into their own files.
Did you say 2380, like as in 2380?
Yes.
Okay. Yes. And this is what's controlling your ESP32. What's this? Is this something that have you used other project code to help you design this, or is this something that you've worked on from scratch, more or less?
So we used this in the last project, which I can bring up right here. This is the 10-foot helical, which is outside.
Oh, that is a very nice antenna. I like it.
So you'll notice it's just a smaller version of this.
Yes. Well, larger.
We like helicals. If I can
is that chicken wire at the bottom?
That is chicken wire at the bottom.
I like it. Gives it a DIY aesthetic. That's right.
And I made a YouTube video about how we made it, and a few people in the comments have said that they want to make their own.
That's really awesome.
So this picture is that, and then, so this code came from that project to track satellites, like the ISS, and talk to astronauts. There we go. So this is the code that controls the LCD screen. So it's not very big, but we have a couple for loops right here to control the when you click on things, so it will nicely pop up. And I'm using the LVGL library for all of the aesthetics about that.
No, interesting. It's got its own calculates it based on the body that you've got, the astrological body. This is very interesting. And can people find this code on your GitHub? Is this published, or is this something that you're still working on?
So this code, there's an old version in my GitHub, which is but the LCD doesn't exist. We added a whole lot of new things to make this work, but haven't pushed to GitHub yet.
And for those of you who are watching this later, we will make sure that links to Zeke's YouTube videos that he's talking about, plus the GitHub repos that we're talking about, we'll make sure they're underneath in the show notes, so you can check back there for them next week.
All right. Can you put that side by side with my video?
Yes, 1 second. I have to take my there we go. Wait, no, I need to take myself off. Nope. I'm gonna remove myself. can put your picture, so I can put that. Let me just see if I can switch it around. I got limited. I can see your code and then your device, or I can, no, that doesn't work. This one or that one, no. Okay, and the only thing I can do is I've got this little, you can, or I'll remove myself and you'll be able to just see the smaller picture and screen with your code at the top. That's the layout.
All right. So this is how I control it. We have status here, and that controls all of the positions for this. And that's based off of the GPS module over here, which gets its GNSS signals for very accurate positioning for tracking satellites. So if I do sat track 1, whatever 1 may be, actually, so let's not do 1 ISS. There's a few ISSs. Sorry. And so now it's going to track the International Space Station, but it can't go below -45 because we'll hit the this component here, which is the accelerometer. So we can't really go below -45. But now it's going to track it. It has to get to 31 degrees. And because there's a metal bar under the table, it's magnetic, so it won't be correct. Oh, great. All right, maybe let's track something else because it's really not working. Anyway, so that's how I control it from my screen.
Yeah,
and
that's really awesome.
That's also how I control the big antenna outside, so it can just track things.
Oh, right, you should control that in the same way. That's really cool.
Yeah.
Very cool, very cool. And thank you for
the same code, just modified for this.
Yeah. Well, thank you for sharing your code there and giving us a little demo. I mean, live demos never work, but we did get to see your code in action, so that's you did better. you did better than most live demos, for sure. Okay, so we're nearly at we're not that long away from the end of our hour. So I did want to ask you. I wanted to ask you a couple of questions that I didn't get to ask you yet. I was going to ask about the Lego rotor, the Lego version of your rotor, and ask you why you used Lego in one of them. Was it for prototyping, or was it just for fun? Or curious to hear about your materials choice for your Lego rotor.
All right, so I have to ask you a question about your question. Which Lego rotor?
Well, I know that you have several, so I was hoping that you might expand on the few that you have, because I've seen a few of your videos that show off a few of the things. But just like many people haven't probably seen TinkerCAD used in the way that you've used it today, I don't think many people will have seen people using Lego in the way that you're currently using Lego. So I definitely wanted to get people to show off your interesting Lego usage.
Here we go. So this is my original Lego tracker, and the Lego tracker here is kind of hidden, so I have to move the camera at a weird angle. However, this rotor at the bottom of it here, it was, I have a stick somewhere. Stick. A pointing stick.
A pointing stick.
Yes. So this rotor at the bottom of it used to control the big antenna outside, except it was too weak. So it became the test bed for that big antenna outside. And then I have another Lego tracker here, which uses the EV3, and so that's this, and it can track only one satellite, the ISS, and it never got developed because I was going to put it on Lego and try to make a Lego set out of it, but if I did that, then Lego would gain the credits to it. So this is just a model for me.
Yeah. And for those of you that aren't familiar, the Lego EV system, it's basically like an ecosystem of robotics that's compatible with Legos, right?
Yeah.
And you can do a lot with it using Scratch or Scratch-like systems, correct?
Yes. However, it's also programmable in C if you use EV3 Dev. So that is how it's programmed to track satellites.
Yeah.
It's basically the same code I have here, just very, very simple.
Yeah, that's pretty awesome.
Because it can only track one satellite with one TOE. And then I can share my screen on a different thing because there's another rotor.
Another Lego rotor.
Another Lego rotor, yes.
You're spoiling us. You're spoiling us. Multiple Lego rotors.
Showing you all the Lego rotors.
All of
if
them.
I can find it. If there's a lot of pictures. Oh, Zeke's antenna rotor. Here.
Nice.
Nope, different antenna rotor. Let's see here. I may have a rotor. What's it called? Aha. Is that it? No. Arrowing through pictures. Like I know there's one there's in here. Actually, there's two. And there's like 100 pictures. Okay, well, I'll show you this one to start. You know how I said back to my share screen?
Yep, got it.
So you know how I said that rotor there used to be used to control the antenna? Well, this is how it was used.
Yeah.
It was just sort of jammed onto the side of our deck and connected with that same motor right there. And it's got a little worm gear.
That looks so fun.
Because I have lots of rotors. Here, let's see if I can find this.
I like your kind of DIY environmental shield. What is that made out of? Like your enclosure?
Some plastic carton from something.
Yeah.
Zeke's
very something. DIY. I approve.
Rotor. Which? Come on, rotor, please, rotor. No. Okay, I'll get it from a different place.
Well, we could, if you don't want to continue looking, we could move on as well. We've got, I do have other questions that I'd like to ask you.
Okay.
I do only have a
go
couple
ahead and
minutes
ask
left.
me that while I pull it up.
Yeah. So, well, first of all, and I was wondering you don't have to have an end goal, like learning is amazing just for learning's sake, but I was wondering, like, are you intending to work in the industry? Like, are you looking to design your own hardware and start a company, or do you want to work for NASA, or do you have like any ideas about where you'd like to take this exploration?
So for my desktop satellite tracker, I'm planning on selling it.
Mm-hmm.
So that... I'm also interested in becoming a pilot.
A pilot, okay. Yeah.
I have a flight simulator under my desk.
Nice.
And rudder pedals and a bunch of other things. And I usually use a laptop for it. So I think I have pulled it up. Oh, here's a good picture.
Okay, tell me when you got it.
Screen. This is my Cadence Live presentation. No, this is my DAC presentation. The Design Automation Conference.
Yeah.
It's pulling it up. Moxon antenna, Lego rotor, other Lego rotor, please.
Right, you look a lot younger in that picture.
Yeah, that was from a long time ago. Here is the other Lego rotor.
Mm-hmm.
So I don't know if you can see it, but underneath all the skiers here, there is a Lego rotor because the original AC motors did not work. They were frozen, so I had to replace those. And then here's the other Lego rotor.
So it is.
There's the gear there.
Yeah. I do see that. Very cool. And that works pretty well?
Yeah, so these are very old motors, and they're still outside working today, so
they do look very old, but they don't look like there's a lot in there that can go wrong. It's very cool.
Yeah, the problem is this does not work at all with Firefox, so
oh wow.
This is our rocket board to control it. in my screen.
Oh, you etched that one yourself? That's great.
Yes.
I love to see an etched, a DIY etched PCB. Very cool. Where did you do that? At home?
At home in the garage.
Nice. Very cool. Lots of fun chemicals to play with, I guess. It's adequately dangerous to be exciting.
If you go back to my camera, there's the real built.
Here we go.
It's here.
Yep.
It's right here.
Nice.
So that's that circuit board.
That's real cool.
It's not tracking right now. It's just plugged in. So
yeah, very awesome. Very cool. All right. Well, Zeke, we've been speaking for an hour now. It is 1 o'clock, which is the end of my show normally. Let me just take this off and put you back on. Where are we back? Here we are. There we are. That's both back on. So we've already been speaking for about an hour. I've still got like a bunch of paper notes on my desk of questions that I didn't get to ask you, but that's okay. I had a really nice conversation with you anyway. It was really fun to learn, and I actually really did learn some tips that I will take forward today. So before we sign off, is there anything that you'd like to ask from people who, are you looking for contributors to your GitHub? What do you want people to just subscribe to your YouTube? Like how can people find out more and keep in touch with you? And B, is there anything you'd like to ask for in terms of expertise or, help?
So the OreSat question about getting a picture from OreSat.
Yep. I will ask Andrew that. So fire away.
And that's pretty much it. We haven't gotten a picture yet, and I'd like to know why. So,
but you haven't managed yet to speak to somebody on the ISS.
Oh yeah, that. So I am working on getting an AIR's proposal so that we can do that.
That would be really cool, ISS speaking. All right, well, it has been absolutely delightful speaking with you. If you'd like, Zeke, you can stay on the line after I hang up on all the internet viewers, and I can say goodbye to you then. But I just wanted to say goodbye to all of our viewers. Thank you so much for joining us and your curiosity. Thank you so much to our guest today, Zeke, and again, shout out to our sponsors of today's stream, Qorvo. We do have the next stream that is the next stream live will probably be with Joey Castillo talking about his open source Kindle alternative, the Open Book. But I will keep you updated because we need to make sure that he's ready with his prototype before I do that. So thank you so much for joining us, everybody. I will make sure that we put Zeke's details down in the show notes, and they already are actually there. So if you want to go and follow him, you can just click on the show description, and the first thing you'll see is Zeke's YouTube handle. So do go over and make sure that you subscribe and press that like button and notify and all of that stuff. So have a great week, everybody, and have a nice weekend, and I will speak to you all again soon. Thanks. Bye.
Bye.